it allows you to program the board very, very easily. Anyhow, so that's there in case you're interested in doing that. And I've got a devoted page specifically for the JTAG interface explaining what it is and all the different features that it supports. So definitely check it out. I've even got a video in there for you to look over if you're interested. And so that's for the real diehard fans that are interested in doing some a little more intricate interfacing with CPLDs and FPGAs. So now, again, I have to announce that because this is a college and university project, it's a very common, popular project for professors to choose as part of an engineering or electronics course. I'm not going to be providing full-blown VHDL source code files for you to just download a copy and submit to your professor and just not doing the work. So I'm not going to be doing that. I'm going to be focusing on trying to deliver the fundamental concepts of a VGA controller to you and explain things in layman terms and use different analogies to try and allow you to understand what's actually going on and how the signal requirements are created for doing VGA interfacing. So that's this project. Now, because a lot of you in the past, for all the tutorials that I've done in the past, I've just been bombarded like unbelievable amount of emails and YouTube post messages that I've received, people asking for help and questions with either code or ways of doing things, working with different projects. And to be honest, the reality is I just don't have the time with work and regular life and doing these tutorials. I just don't have the time to go and answer 50 emails a day to try and help everybody. So what I recommend is that you join this EDA board forum, and it's a devoted forum page for CPLD and FPGA digital design. And so it works all around working with all the hardware of FPGAs, CPLDs, but also with all the different programming aspects, so VHDL, Verilog. And you get all these professionals, engineers, teachers, professors from all over, different students, and it's just a whole group of people all working in the same areas, with areas of FPGA programming, and helping each other out with different projects that they're working on. So I definitely recommend you register on this particular forum and submit your questions, and you'll be really surprised how many people group together to help each other out. So I definitely recommend that you register and start posting your VHDL questions there, and you'll get a lot of help. It's a really great asset to have. So anyhow, so that sums up my first video. The next follow-up video, I'm going to be going right into the VGA interface and talk about the fundamental concepts and how that works, and then we'll move on from there. So I'll see you guys in the next video. Okay, folks, so welcome to part 2 of my Ultimate VHDL PON tutorial. And so to start, we're going to be talking about the VGA interface and the signal requirements for that. So anyway, essentially the VGA standardized interface and the signal requirements for that came out and were released by IBM back in the late 80s. And essentially the standard signal came out to drive CRT-based computer monitors. And so the cathode ray tube based like old televisions, the signal came out to drive these particular types of monitors. And that particular signal standard actually ended up becoming adopted by later LCD-based monitors. So even though liquid crystal displays require a specific type of signal to drive them, because the infrastructure for computers had been set up for CRT-based monitors, LCD monitors just adopted this particular standard. And so that happens behind the scenes. It's all done with internal circuitry. We don't see it, and we don't have to worry about it. So we can still apply a VGA-based signal to an LCD monitor. So I'll talk about the VGA signal standard a little bit. With our VGA signals that we're sending in, when we're talking about the CRT-based system or cathode ray tube-based monitor, this is actually a very high voltage system. So you're talking thousands of volts that are required to power these electron guns, which essentially emit different intensities of electrons to essentially control the amount of color that is generated on the screen for red, green, and blue. And so we have an electron gun for each color of R, G, and D. And then different combinations of those together and at different intensities, we can control what color is displayed on a particular pixel on the screen. And so essentially how it works is we send in a low voltage, and that gets translated into an extremely high voltage for the electron gun. And then these beams of electrons get sent out and cause a reaction with phosphor-coated backing on the back of the monitor screen and emits light. And then we have what's called a shadow mask, and all that essentially acts like a filter, which essentially controls which colors, which electrons, the beams of electrons that get sent in from R, G, and D, which ones get penetrated through to generate specific colors of light that we want. And now without some type of control for these beams, the beams would just shoot off into the center of the screen. So we actually have a couple of electromagnetic coils that are used. One is used to control focus, and the second grouping of electromagnetic coils are used to control the aiming point or the position of the beam on the back surface of the monitor. And so And so really, when you think about it, the signals that we're sending into these deflection coils are essentially our H-sync and V-sync signals. And these signals are used to control at which point the RGB beams are focused on the screen. So you can sort of look at the back of the screen almost like an XY coordinate system, almost like on an Excel sheet. Pardon me. I've got this little graphic here that I found online. It sort of helps to demonstrate how the beams work. And so by sending in specific signals, the H-sync and V-sync signals to these deflection coils, we can actually control what's called the refresh scanning rate to the back of the monitor, and essentially control the resolution setting that we want to display on the screen as well. So you end up having this, essentially the H-sync and V-sync signals, you can look at them almost like XY coordinate counters, essentially. And so you have a particular signal that's sent in, or like a counter for the X and a counter for the Y, and a specific coordinate that we send in on the H-sync and V-sync signals essentially determines where the beam is focused on a particular area on the screen. And so by constantly fluctuating and changing the H-sync and V-sync signals, we can actually control it to perform this zigzag scanning effect and have the beam focused on one particular point on the screen at any particular moment in time. And so then we create this whole scanning effect. And so by controlling the timing of that, and if we synchronize our control signals that we send into our RGB lines, if we synchronize those with the horizontal and vertical synchronization signal, the H-sync and V-sync signals, we can actually control and create an image on the screen. So it's all about synchronizing really the H-sync signals with the signals that we're sending in on the RGB lines. Those are essentially synchronized, and we have the right color intensity and combination being sent in at a specific moment in time. We can actually control the sequence and create an image on the screen. So it's a lot to take in, but that's essentially it. And so you can really just look at the H-sync and V-sync signals almost like X and Y counters, creating an X and Y coordinate system for a particular position for the beam on the screen. And also just to mention, this graphic that I found is actually showing what's called interlaced frames, and that's where it's actually skipping a line and then continues through and does essentially two passes to create a complete image. But that's not what we're doing. We're actually just doing a standard display. But this particular type of image here is called interlaced frames, or interlaced frame. Anyway, I just thought I'd mention that in case you were curious. So that's essentially how the CRT system works and how the VGA signals, how they work. So we have H-sync and V-sync signals and the RGB signals. So essentially 5 different signals that we have to focus on. And those are shown here on the pinout for the RGB DB15 connector. So we have a lot of ground lines there, but the only ones we have to worry about are the analog voltage pins for RG and D, and then our H-sync and V-sync signals, which all they do is essentially control the resolution setting and the timing and the position of the electron beam as it moves across the screen, and controls that aspect of it. And so now I've got some other diagrams here that you can check out. One that's kind of really cool to check out, and how the D1 board, most of the development boards are interfaced, is that you can actually use a resistor array in order to use just a control bus off of the FPGA or CPLD to create different intensity levels on each of the analog RG and D lines, and that generates the different brightness levels of your color. So by sending in specific patterns of a binary number onto the interfaced pins to the resistor network, we can control the analog voltage level and then generate different levels of intensity of the color. So that's good to know. And our D1 board has that particular setup, but we're not really going to be doing different intensity levels, but it's there in case you want to try doing that. So again, just to review, it's best to look at the H-sync and V-sync signals almost like X and Y coordinate system. If you can picture it that way, that's the best way to do it. And all that's doing is controlling where the beam is focused on at a particular position on the screen. So H-sync and V-sync controls where the beam is at any particular moment in time. And so I've got some images here for you to check out from the Rapid Prototyping of Digital Systems manual, the textbook, and it talks about that coordinate system. So you can definitely check that out. It's good to know. And so now, at this point, we're moving on into our VHDL circuit, and this is the circuit of various VHDL blocks that create the complete VGA controller and our Pong game. And so that's going to be our next video, and we're going to be talking about that. So we'll see you guys in the next video. Hey folks, just putting together another video for you here, another instructional video with Minter Graphics, HDL Designer, and ModelSim. So today's video I'm going to be showing you how to implement some custom-made buttons into the Wave simulator window as part of the ModelSim program. So now I know a lot of you have been asking me to help post some videos specifically for VHDL programming for different projects that you're working on. A lot of you were asking about the stepper motor driver program, FPGA project, and I know there was a number of you actually talking about the VGA decoder program, and a lot of you were having trouble with that and understanding the different areas of the functionality and how it all works, and leading into displaying graphics. A lot of you doing a Pong type video game or different types of displaying graphics games or whatnot. So, time permitting, I will try to post some videos on the different areas of how that works and just sort of showing you the fundamental concepts, just so that you get a better understanding of what's actually going on and how the code relates to all the different areas and different functionality of a decoder. So, time permitting, I will try and post some more videos just to help you guys and help guide you in the right direction and provide a more thorough understanding. So bear with me, time permitting, over the next few weeks I'll try and post more videos within those areas for VHDL. For today's video, I'm going to be showing how to add custom buttons to the model sim wave window. A lot of you were asking me about that, and I had actually had trouble in the past. I tried to figure it out. I'd figured out ways of doing it using the menus of adding buttons, so that when I was to perform a demo for a professor or a TA, I was able to do it in a timely manner very efficiently. So I'm going to show you how to add those in permanently, so that every time you activate your model sim program and you activate the wave window, those custom-made buttons for different run lengths for your wave simulator window will be present every time you activate the program. So to start off, we have here our VHDL code, a typical clock divider. You're probably very familiar with this by now. If not, you'll be coming into it. It's your typical clock event and clock equals 1 clock divider. And there's a couple different formats you can get, but this is the one that I have here. And so anyway, we'll go ahead and run that. So we'll choose our model sim through design root option. And now you'll get your typical start model sim window. We go ahead and click OK. So we go ahead and click OK, and model sim boots up. Okay, so as you can see here, we have our model sim program is activated. We have our port signals here for our clock divider. Now, normally what you would do is you would select a view and select the wave window. And there we go, and then we have our wave window, right? Actually, what I'm going to do here is shift these over just so that we can see these two windows simultaneously for the sake of this instructional video. Okay. So now you'll notice here, so there, if we close this here, so now you can see down here we have a terminal window. This is a transcript window. It notifies you of different functions that have occurred with the software, but it also allows you to type in commands within this terminal to perform certain functions for the software. So the same way that we would select different menus and activate different functions, you can implement those functions and even more functions that aren't necessarily available as part of the menu. You can implement and activate those using the terminal window. So, for instance, if we were to activate the view wave window, from the view menu, we could type view for selecting a view menu. And as soon as you type view, you can see here how there's all these different command options that are available. So there's ways of implementing specific functionalities to those commands. Now, I won't go into that too much, but just know that they're there. And if you decide to research further, more advanced options for using the terminal window, it can be quite handy and allow you to do some advanced functions. Anyway, so we go ahead and type view, and then we select wave, because that's the window we want to activate. And we hit enter, and there we go. It brings up our wave window. So just a demonstration there to show you how the terminal window can be used. So now, some of you may have figured out that you can add buttons based using some of these menu options. You can add buttons yourself to the toolbars. But then what would happen would be that every time you would shut down Model Sim, and then you opened up your wave window again, those custom buttons that you had added will be gone, and you'd have to constantly be repeating everything for adding those buttons to the window. And it's just a little bit of a pain. So I'm going to show you here how to implement them into essentially a script, which will then run and it'll add it for us every time we boot up Model Sim. So we have the first command was view-wave. Now I'll show you the command necessary to add a custom button to the wave window, and I'll just describe it here very quickly. So there we go there, and we hit enter, and as you can see, a custom button has been added here. Now, I'll explain here. It's pretty straightforward, self-explanatory. Apply _button _adder is the command function to tell Model Sim what function we're performing, which is adding a button to a toolbar. Wave is the window that the button will be added to. Controls right is the toolbar, controls toolbar on the right side. And then we have our color.